Okay, so this is what a neural network looks like. These circles here are called neurons, like neurons in our brain. And then the lines here in between them are called weights. We'll see why shortly. And they connect the neurons, like synapses in our brain, which connect our biological neurons. We call these columns of neurons layers. So this neural network is a deep neural network, in a sense that it has multiple layers. This is where deep of deep learning comes from. In a future video, we'll see why this is better than a shallow network, which is just a network with less layers. Now, this looks really different from our input function output model, right? So they look nothing alike, but it's actually exactly the same thing. You see this first layer here? This is the input layer. This is where the input comes in. And all this middle part here, in between, in fact, the neural network itself is the function. And this last layer here is the output of this function. And then there's the label, which is the correct answer. And then here's the loss, which tells us the difference between the output and then the label, which means how wrong this neural network function is compared to the correct answer we provided. And we're trying to minimize this loss. When it's 0, that means the function produced the output that's exactly the same as the label, which is the correct answer. See how they're exactly the same thing? Basically, input comes in, this entire thing is a function, and then the output comes out, and then there's a label and the loss. This is just a more detailed view of the function part of our input function output model. Now, there must have been a lot of different ways to make this function part. Why a neural network? It seems like a completely arbitrary architecture for a function. How did we come up with something like this? Actually, there's no magic. We just cheated, in a sense. We were inspired to build this neural network by looking at the structure of the brain and realizing that this is how the brain seems to work. And since the brain can solve pretty much any problem, why not emulate its structure to see if we can solve problems that were difficult to solve using traditional methods like coding? Unbelievably, this crude model of the brain, called a deep neural network, turned out to actually work. As we will see later, the smartest researchers in AI doubted something like this would ever work, and abandoned the approach many times throughout the past few decades. But a few believed in it and persisted. Now we know this neural network function can solve any problem. We can mathematically prove it. And it's called universality theorem, which we will look at in more detail in a future video. Anyway, let's see if we can delve a little deeper and understand what this neural network might be doing. Here's one way to look at it, as a set of features and weights. So these neurons here represent features of data. For example, we might want to predict how much our house sells for. Then we might use the number of bedrooms, age of the house, interior and exterior design quality, etc. as input features. Then in the next layer, we might have bigger features that use the features from the previous layer. For example, this first neuron here in the second layer might be attractiveness of the house, which might use some combination of the bedrooms, age, interior and exterior from the previous layer. And then these lines that connect these neurons together are called weights. A weight determines how important that particular connection is. For example, it might turn out that the interior design matters the most in determining how attractive the house is. Then we might give more weight to this feature, right? So then the line connecting here, this weight, might be higher for this particular connection than any other connection. This is why we call this a weight. See how this might work? Just by defining which features are important to solving this problem, which in this case are features that determine the price of the house, and then determining how much weight to give to each feature, we're able to make a prediction. There are no if statements or for loops we're used to. We don't specify every step of the how. Instead, we solve a complex problem by letting the machine figure out relevant features and their weights laid out as a network of layers. Don't worry about exactly how this network does that. We'll explore that in great detail throughout the course. For now, try to get the big picture of this. Now, this can be done for seemingly unstructured input data, like an image as well. For an image, each pixel would be a feature. It's not obvious at the beginning, But if you think about it, each pixel is a feature of an image because how the pixels arrange themselves determine what the image looks like, right? So we use each pixel as an input feature, and in the next layer, we might use the features from the previous layer to build bigger features. For example, edges like this. And then the layer after that might take these edges and build even bigger features like shapes like this. And the next layer might make more complex shapes by building on the previous layer. And then the fourth layer might use these shapes to identify actual features like faces of a dog, as you can see right here. We're visualizing the actual edges and shapes here to prove a point, but in a neural network, these would just be neurons and connections like the network view we saw in the previous slide. So if we had all those features and weights built out, we can identify if a new image we're given is a picture of a dog, for example. The model will take the pixels and try to match it with the edges and shapes until it ends up with the label of an image, the word dog. So if you think about it, this whole neural network here is really just a function that transforms the pixels in the input image into the label, a word like a dog. See how we're looking at an image as data? We're feeding this image, which is just data of pixels, into this function called a deep neural network, which transforms it to the correct label for that image. Let's quickly recap. There's nothing magical about why a neural network looks like it does. We happen to notice that our brain works that way, and we decided to model after it to try and solve problems. Each neuron in a neural network can be seen as a feature of the data. For example, when trying to predict a house price, the input is multiple features of that given house, like number of bedrooms or the age of the house. Then each layer of the network transforms the previous layer's features into some other set of features. To develop the next layer's features, we use weights to determine how each of the incoming layer's features contribute to a particular feature in the next layer. So weights determine how much weight we should give to each feature. Now this can be done for unstructured inputs like images as well. Now we gave names to these features so that it feels more intuitive, but we don't actually decide what the features and weights are for the middle layers. For example, we said that the first neuron in the second layer might be an attractiveness of the house, but we don't really know. The machine learns the features and weights on their own and decide which ones are relevant. We'll take a look at how this works in the next video.